Okay, the recording has started. I guess we could start, Sean, very early. And then for those who, let's just catch up. During the introduction, I usually go through some rules and regulations. So if this is your first time in one of our tech training calls, so just for your information, that this has been a series of tech trainings for the past few weeks. So this is training number 7 out of 7. So what we're going to talk about today is we're going to be joined by our esteemed trainer, John Bryant from Mammoth Geospatial, and he will be leading some QGIS analysis and techniques for some specific use case scenarios. So I think we are going to pass through flooding, landslide, and tenure, but I'll leave it to John later on to discuss it more. For those who are here, this is a safe space. So please feel free to be very courteous, very kind when you're giving out comments. And FYI, I have muted everyone because we are expecting an influx of participants so that John doesn't get distracted for his session and he could focus on presenting. I have muted everyone. So if there are any questions, please feel free to put it in the chat box. I will go through the chat box and John will be opening up time later on for questions and I will be asking them. So feel free to add your questions in the chat box. If there are any questions that our participants can answer, feel free to jump in. This is an open space as well. We are all experts and we are all beginners. So feel free to jump and write in the chat box. Lastly, I am recording this session for the benefit of those who will not be able to join. So if you do not want to be part of this, will feel free to watch the recording later on. Anyway, yeah. Finally, I'll just go through some minor slides here. So as I mentioned, this has been a part 7 of the 7 tech trainings we're doing here. So as we all know, contributing to geospatial data, open map data, there's a lot of entry points that we could do. But through these training sessions, which all have been recorded, you can see here that those entry points could be in drone imagery capture, in remote desktop mapping, in AI-assisted mapping, in projects wherein you involve field mapping tools. Once you collect that data, there's several ways that it goes through OpenStreetMap or QGIS, or you could use it personally directly as it is. But there are several ways wherein you could access and visualize OpenMap data. So, and last week, John also was here and shared some basic QGIS analytic tools to know where the gaps are in OSM data. So as you can see here, we're doing an end-to-end user case wherein we're going through these different entry points throughout the training sessions. So for today, our since this will be our last tech training for this month, hopefully we will be getting a lot of questions and hopefully we can be enlightened how the connection between drone imagery up until using it to QGIS gets connected all in all. Lastly, we will be sharing a feedback form at the end, and I hope everyone could mention there what type of other trainings we would like to request, because we found out that these trainings have been very beneficial for not just open map community members, open mapping enthusiasts, and many more. So I'll be passing the floor to you now, John, and yeah, I'll just be here around whenever you need me.
Okay, well, thanks a lot for the intro, Miko. Let me just share my screen. All right, you can see that? You can hear me? Are we good to go? Oh, cool. Okay, thanks. So welcome, everybody. Thanks so much for having me, and happy Friday. So my name is John Bryant. I'm here to talk to you about QGIS, and talking about QGIS is one of my favorite things to do. So yeah, thanks again for having me here and for spending the time with me tonight. So just to introduce myself, I grew up in Canada. but I live in Fremantle, Western Australia. And I love the open geospatial community. So I'm heavily involved as a volunteer with groups and events like GeoGeeks, OpenStreetMap Fiji, FOSS4G Perth, FOSS4G Oceania, OSGeo, and OSGeo Oceania. I work with open source geospatial as well. I started my company, Mammoth Geospatial, so that I could focus on open geospatial. And we do consulting and training, and we help people around the world with QGIS, PostGIS, GeoNode, and other open source GIS packages. So I've been doing GIS for a long time. I started off a long time ago with ArcGIS, and I've been using QGIS since about 2007. And these days, I use it every day. I'm always learning new things you can do with it. And so I'm a certified QGIS trainer. And like I said, I love sharing the joy of QGIS with people. So anyway, really stoked to be sharing this session with the HotOSM mapping gurus, even if it's a little bit intimidating. So moving along, what we're going to do in this session. So we're going to work on a terrain-based flood susceptibility analysis with open elevation data, the SRTM elevation data from NASA. And we're going to use that data to do a hydrological analysis of the terrain. And we'll look for buildings and roads that are susceptible to flooding. And we'll use the OpenStreetMap data for that. So I guess important for me to say that I'm not actually an expert in hydrological analysis or flooding. So take this with a grain of salt. I'm more of a GIS generalist, but basically I want to show you a method that you can use just about anywhere in the world using completely free data and software. So this will be, we only have just under an hour and a half now, so this is going to be a really quick walkthrough, but we're going to start from scratch and work our way through to analyzing flood risk and relating it to buildings and roads in the landscape. And if there's time at the end, hopefully we'll have a couple of minutes, and if we do, we'll take a very quick look at using Sentinel satellite data to map flooded areas. So, so talking about flood risk in low-lying areas. So the concept is, and a lot of this may be very intuitive, but I just want to talk about this for a minute. So the concept is where streams flow, where water flows. So this is the position in the landscape where the soil is permanently saturated. So for areas near these stream flows, soil saturation levels are influenced by their height above the drainages. And so for areas higher up in the landscape, relative to stream flows, have a lower risk of flooding than low-lying areas. And areas down low, relative to the nearest drainage channel, are more likely to have a high water table, more likely to become saturated and be impacted by flooding. So essentially, there's a strong relationship between terrain or elevation and flood risk. And so what I want to do here tonight is walk through using QGIS to explore this relationship and use it to predict flood susceptibility and again, identify buildings and roads at risk. So I'm just going to switch over to QGIS here. So as you can see, starting off with a blank slate, and I'm just going to bring in a couple of data layers to get us started. So first off, our area of interest. And I'm just going to bring in a couple of base layers here just to put it in a bit of context. So we've got, I might just make that a little bit less opaque for a moment. Okay, so we're looking in the East Sepik region of Papua New Guinea. Again, if you were here last week, this is the area we're working in then. We're working in the same area this week as well. Part of the reason I'm interested in exploring this area is because it's the topic of a few HotOSM tasking manager, urgent tasking manager tasks. So I think it's a relevant and interesting area, and also very, very, flooding is something they've been experiencing recently in this area. So quite topical and I think relevant to this group. So, so this is our area of interest. And I'm just going to add some OpenStreetMap buildings. And so my source for the buildings data is GeoFabric, I mentioned it last week. This is a really nice source for nightly extracts from OpenStreetMap, divided into countries. So this is the Papua New Guinea extract, and I'm going to bring in the buildings for PNG. And I may just make the borders a little bit heavier, just so they show up better at different scales. There, that's a bit better. Okay. Okay, so that's my basic setup. I'm just going to save that project in my temp folder, and I'm going to call this flood risk analysis. Cool. All right. So, so we're doing a terrain analysis. So I need some elevation data. And my go-to for elevation data for just about anywhere in the world, if I don't have anything more detailed, is the SRTM. So I'll just briefly show you. So SRTM, Shuttle Radar Topography Mission, this comes from NASA. This is an elevation map of almost the entire world that was taken from the space shuttle in around the year 2000. So it's some great things about it. Like I said, it covers nearly the entire world, which is awesome. But it has some limitations. So one of the limitations is the resolution of it. It only has 30-meter pixels. I believe it's like one of the best DEMs you can get for free. But if you have if you have better data for your local area of interest, then you should use that, because this is a little bit coarse for very, very zoomed in analyses. However, like I say, easy to get, readily available. So another potential shortcoming, it was captured over 20 years ago. So in some cases, rivers move across the landscape. So yeah, just something to be conscious of. If you've had major landscape change in your area of interest in the last 20 years, then you'll just have to sort of take that into account while you're using this data. So my usual go-to in QGIS for getting SRTM data is the SRTM downloader plugin. So I just want to show you that momentarily. So SRTM downloader, free plugin. QGIS is free. The plugins are free. Everything we're talking about here is free and open. So this downloads the tiles. They come in 1 degree by 1 degree tiles over most of the Earth. And they come from the NASA server. So I'm not going to download these directly because I've already got them downloaded. But I'll just mention before I do that when you install the plugin, it becomes very easy to get these tiles for your area of interest. You basically just zoom to it, click on this new button on the toolbar, SRTM downloader, set your canvas extent, click on the download button. And if you don't have a login yet, you'll need to go get one. It's a free login from NASA, but you can download, once you log in, you can download all those tiles. So rather than wait for those to download, I've already got them. So these are the 6 tiles that I'm after that'll cover my area of interest. So I'm just going to bring those in. And so, yeah, so a few things about these layers here. So as you can see, they come in these 1 degree by 1 degree tiles. They're covering my area of interest. And if I zoom in, you can see what we're working with. So this is raster data. Each tile, here I'll just look at one at a time here. So each tile covers, like I said, a 1 degree by 1 degree space. But if you zoom in, you can see the pixels, and each pixel has a value. If I click through them, you can see the values changing in this Identify Results panel. So each pixel has a value that refers to the number of meters above sea level. So it's an elevation model. Every pixel is meters above sea level. And if I take a look at a couple of them next to each other, you can see there's a little bit of a seam between them. And so the reason for this seam is not that the data is different on one side or the other, but really just that each tile, when you bring it in, is styled a little bit differently. So the 142 one here has a range from -8 to 1,556. The one next to it has a range from 0 to 1,118. So the style just comes in a little bit differently between the two. And so it can make it a little bit cumbersome to match these up and to make them operate seamlessly. But I want to show you a way we can stitch these together because ultimately what I want to get here is a nice clipped out DEM just for my area of interest. So I've got my 6 tiles here. I'm going to make a virtual raster out of these 6 tiles. And so virtual raster is basically, it's a little wrapper around these tiles that points at the data sources for the tiles and combines them into a single raster. So I'm just going to use a tool in QGIS under the raster menu, miscellaneous, build virtual raster. And so this will bring those 6 tiles together. I just need to choose the layers that I want to stitch together. So I can just drag and drop those from here. So those are my 6 layers. And I don't really need to do much more than that. I'm going to save it as a temporary file because I know that I'm going to have another step after this. So I'm just going to save it as a temporary file, open it in QGIS. If I click run, I can see that's already done. And so I turn those ones off. Now I can see this new virtual layer here combines those 6 tiles into a single raster. And seamless as well. So I'm no longer seeing those seams along the edges of the tiles. So we're partway there. The next thing I wanted to do is to just bring that AOI layer just above it. So I want to clip this out so that I'm just doing my analysis on our particular area of interest. So if I go under raster extraction, I can clip that raster, the virtual raster layer, using my AOI as a mask layer. So I'll do that. Clip my virtual. The mask layer will be the AOI. And otherwise, everything should be okay here. I can just leave it. I can leave the defaults as they are. They're fine. The one thing I want to change here is I actually want to save this as a file. So I'm going to call this srtm AOI. And I'll run that. Cool. All right. So there we go. There's my clipped raster. Just bring that down underneath there. And I can remove all of these tiles in the virtual raster because I'm pretty much finished with those. Okay. All right. So I've got my raster. It's all black and white. I actually want to change this a little bit so I can get a little bit more of a feel for the actual terrain in the area. So I'm just going to open my layer styling panel. And so by default, when you bring in a raster into QGIS, a single band raster, it'll come in with a single band gray renderer. So I want to change that single band gray. I don't want to just see black and white. I want to see some color in there. So I'm going to change that to single band pseudo color. And I'll change my color ramp to something like spectral. And I'll just do a little bit of panning around and zooming. So that helps bring out the texture of the landscape a little bit better. One thing it does do is it shows the differences between the low-lying areas and the more mountainous areas fairly well across the whole area of interest. But what it doesn't do especially well is show me the sort of more localized differences. So one thing I can do to kind of highlight those is use the raster toolbar here. And the button on the raster toolbar that I'm after is the local cumulative cut stretch. So that's just going to take a local area, so the area of my map canvas here, and stretch the pixels so that the minimum and maximum are contained within that window. So if I click on that, watch the legend in the layers panel here. When I click on that button, if I click on that, I can see the min-max for that raster gets adjusted, and I can see much better the texture of the landscape within my particular map canvas window here. So this, I always find this is a really good way to kind of get a feel for my raster data sets when I bring them in, to sort of zoom around a little bit, click on that button and sort of just re-stretch the raster for the map window as I go, because you may want to see the overall texture for the area of interest, or you may want to actually see sort of the more localized um, differences in topography. So, okay, so I've got my raster, everything's great. At this point, I want to start kind of taking a look at how I can use this to help kind of start identifying some low-lying areas where the water table is higher, where the flooding is more likely. And the first way I want to explore doing this is a very super simple method. I don't need any special tools. I don't need to run much in the way of analysis here. I can just sort of use what I've got right in front of me. And so I want to take a look in the bottom right corner here. So where the Sepik River comes through in the southeastern part of this area of interest. I'll just zoom into that area and re-stretch my raster for that. So I can see clear as day that Sepik River kind of sticks out. Maybe I'll zoom in a bit more and re-stretch again, and even more so it sticks out. And so what I can do here, I can use my Identify Features tool, and I can click on specific locations. So if I click on the river in the very low-lying areas, so we're very near the coast. We're very near the main sea level there. And in fact, when I click on it, I can see the elevation of the river is 0 meters there. So it's very low, and the areas around it are also quite low. So 2 meters in this water body over here. As I move my way up the river, I can see slight color change there. If I click on there, stretch that again. As I move up, I can see the elevation going up. So I guess my point, what I'm trying to do here is I'm looking for a simple way of identifying where low-lying areas are near the river. And so what I can do, I stretch it, I've done that. I want to, if I click on the pixels going away from the river, I can see they're also quite low, 4, 5, 7, 3, 4. So these are also quite low-lying areas. And as I get farther away, I can see the elevation goes up. So quite intuitive, quite self-evident. But if we use a method of hiding the higher elevation pixels, we can sort of get a very quick visualization of where the low-lying areas are. And so I want to go into the layer styling panel for that layer. And I'll go into this transparency tab. And one thing I can do is I can set some custom transparency options. And so I can add a set of transparent pixels. And so if I say, well, I want to make all the pixels above a certain elevation transparent so that the low-lying areas stand out, I can say, well, let's hide everything from, say, 15 meters and up. So that'd be, I think, 1500 ought to cover it all. So, okay, so everything above 15 meters is now obscured. I can see this sort of everything, all the pixels that I'm seeing now are below 15 meters, or maybe I want to make it a little bit lower, 10 meters. And so now we're seeing everything sort of in this area that you might consider to be low-lying. So the problem with this approach, it's very simple, it's very quick and easy, but the problem with this approach is it only works right here. So it's very localized. I can't, for example, if I start heading up the river, if my baseline here is 9 meters, well, I can see that these areas are no longer considered low-lying. So I need to sort of rerun my transparent pixels. So maybe now I need to say, well, everything below 20 meters is considered low-lying because it's relative to that baseline of the drainage. So maybe even 25 or 30. And the problem, so now if I want to do work up in this area, for example, I need to go and get the elevation of the drainage there. And again, make my transparent pixels relative to that. So that'd be like maybe more like 100 pixels and up. So I can see where the low-lying areas are now relative to specific locations. But this is because I'm using kind of a simplistic approach with a DEM that is measured in meters above sea level. So might work great down near sea level, but if you go farther up, you need to sort of keep adjusting. Not really great. So what I want to do next is kind of take it a step further and look at a method where we can consider thresholds that are actually relative to the nearest drainage across the entire area of interest. So I want to take a look at this this method here. So this is a slightly more sophisticated method where we actually normalize that elevation model relative to the drainage network across the entire area of interest. And so this height above nearest drainage method, so this is based on a 2011 scientific paper. And in their words, the hand model normalizes topography according to the local relative heights found along the drainage network. And so this method is used for calculating sort of a topographic index of locations relative to their sort of vertical up and down proximity to nearby drainages. And it basically generates a new type of DEM where each pixel value doesn't represent the elevation above sea level, but the elevation above the nearest drainage or stream flow. So again, I'm not a hydrologist, I'm just a GIS person. There are many ways to analyze flood risk, and this is just one way. But basically what I want to do here is use this method to illustrate the power of spatial analysis in QGIS. So I want to describe the workflow here. And we're going to actually go through these steps in detail in QGIS. So this will, so we're going to look at this a little bit deeper, but I just want to take a quick overview to begin with. And so going left to right here, it's a 4-step process. And we need to start with a DEM. And basically it's the only input we need for this analysis. So we've begun with our DEM already. So we're already on the way. And we're going to run through these 4 steps. And as we do it, we're going to use a set of tools, a library of tools called Whitebox tools. So this is a free and open source set of tools. I'll go into that in a little bit here. But for each step we do, we're going to use a tool, we're going to use a tool from the Whitebox tools dataset to run each algorithm. So I'm just going to walk through these. So to go from our DEM to, for step 1, we're going to breach the depressions. And so what I mean by this is we need to pre-process the DEM for flow analysis so that we can do a hydrological analysis for it. So I want to show you another slide here. We'll come back to this one in a sec, but I want to take a look at this in detail. So when we say breach depressions, what we're talking about is there are depressions or pits in the DEM, and they may be from just anomalies in the data, or they may actually be actual low-lying like sort of depressions in the landscape that the DEM is accurately depicting. But the problem is that these can interfere with determining flow directions in a DEM. So the idea is when you analyze a DEM, basically what you're doing is sort of modeling where water will flow. And so it always has to have somewhere to go downhill. And you can see in this diagram here, if you have an area where there's actually a pit, water would in theory flow into that pit and then it would no longer be able to flow downhill. So when we run our flow analysis, it would have problems with that. So what we have to do is kind of precondition the DEM so that we kind of smooth out those depressions, make sure they're smoothed out such that when we run our analysis we can figure out where the water is actually going to flow along the landscape. So that'll be step 1. It's taking me way longer to actually talk about this than it will to do it, but anyway, I'll carry on. So step 1, we'll run a breach depressions analysis. And in step 2, we'll use that processed DEM to calculate flow accumulation. And so we're going to use the D8 flow accumulation algorithm. And what this means basically is we're going to determine the flow pathways along the DEM. If water was dropped onto that surface, where would it flow? And we're going to measure the accumulated flow along these pathways. And so let's take a look at that in a little bit more detail. So this is the D8, what did I call it? The D8 flow accumulation algorithm. And so D8 basically just means deterministic 8-cell, which basically means if you're looking at a group of cells or pixels in the raster here, for each cell, this is the one in the middle, for each cell, what we want to do is model or find the steepest downslope neighbor. So which cell, basically this will figure out which cell of the 8 that are around it, which cell is water going to flow towards. It'll be the one that is the farthest below it. It's going to go on the steepest path. And as you move down the landscape, the flow will accumulate. And so it does the math, it adds up the accumulation along the way. And so again, we're going to see this in a lot more detail when we actually start running the analysis. But yeah, so that's step 2. Step 3 is we're going to take that flow accumulation raster that we create. In step 2, we're going to take that raster and we're going to extract the drainage network. And this is nice and simple, but the concept here is basically that we need a clearly defined set of drainage lines that we can then do our final step with, which is where we calculate the hand or the height above nearest drainage. And so in this fourth one, the height above nearest drainage raster, basically what it does is it takes the input DEM and measures the height of every pixel relative to the nearest downstream flow path. And so it measures the difference between those two and calculates that height above the drainage. And so the end result of this 4-step process, this analysis, is this new type of normalized DEM, measuring the height above the nearest drainage rather than above sea level, which then we can use to model, ascertain, think about at least our flood risk. So let's run through the process in QGIS, shall we? Where's my QGIS? There it is. Okay, so first I'm just going to kill this transparency and we'll re-stretch that DEM, clear those out. Okay, so I said I wanted to use a tool set called White Box Tools. And so this is installing this so that we can use it, take 3 steps. The first step is so it's not enough to just install the plugin. You actually have to install an executable. It's not as hard as it sounds. Basically, you head to whiteboxgeo.com, download the free software, the free program, and then save it to somewhere on your system. Unzip it, save it to somewhere in your system. It doesn't even need to be installed. It's just a standalone executable. So head to Whitebox Tools, download that. Step 2 is to install the Whitebox Tools plugin. Whitebox Tools for QGIS plugin. So you can download it from there. You can also see when you go there, you can also see a bit of information about some links for more information to the manual and so on. Very well documented library. So install that plugin. And then the last thing you need to do, the third thing, is to actually tell the plugin where to find the executable that you downloaded. So that'll be in your user settings. So under settings, options, in the processing tab, under providers, looking for Whitebox Tools, and you just need to give the path to that library that you've downloaded. So that's where it is on my system. The folder that contains the executable is there. So if I click OK, now that I've installed it, I should be able to see in my processing toolbox, I should be able to see a new set of processing tools called Whitebox Tools. Okay, so these are the tools we're going to use to run this analysis. And most of them are in this hydrological analysis group. And so we're going to run through these 4 steps in series and I'll talk through them. So step 1, just to refresh our memory here, breach depressions. We're going to use the breach depressions least cost tool. And so there it is there, breach depression's least cost. So I'm going to open that tool up. And so what is it? It removes any local depressions so that we can determine the drainage network. So my input DEM file, SRTM AOI, that's the SRTM that I have. And I'm just going to save that to my temp folder. I'm going to call it, I can call it anything I want, but I'm just going to name it after the name of the tool just because it helps me remember what each raster is as I go through them. So I'll save that and then I'll run it. And this will take 10 or 15 seconds to work its way through, processing all those pixels. And it's done. So close that. And we've got a new raster here. And so this raster, breach depression's least cost. So I want to do a little bit of a comparison here just so we can get a sense for what it's done. And so I'm just going to zoom in to an area here, and I'm actually going to copy the style from my my DEM, my SRTM, to that layer, so that they'll be more or less identical. And so maybe if I pan around a little bit, I'll be able to find somewhere where it tells the story nicely. I'm going to stretch both of those in the same area, and I'll just toggle these on and off. Okay, so I can see as I toggle them on and off, or as I toggle the breach depressions one on and off, I can see some slight differences between the two rasters. And maybe I'll take a look and pick on this area here. And so what I can see, this is the original SRTM. We can see in this, looks like a relatively low-lying area. It's quite lumpy. And so what we can imagine, these are lower locations of elevation, little depressions. And so what it's done is it's smoothed them out. It's kind of basically filled them up so that when we model water flowing across this landscape, it doesn't get stuck in those pits. Okay, so that's step one complete. Let's move on to step two. And step two is this D8 flow accumulation. And so let's find that tool and run it. And so there it is there, D8 flow accumulation. And so my input DEM will be the breach depression's least cost raster that I just created. I don't need to change any of the defaults. I'm going to save that to my temp folder and call it D8 flow accumulation. So if I run that, so it's going to run over that whole landscape, find all the possible directions of flow, accumulate all the flow across as it moves into those channels. And it actually does it very, very quickly considering what it's done. And so now we can see with this one here. So this one's a little bit different. This is not an elevation model. This one is, and if I stretch that one sort of in a local area, it becomes a little bit easier to see. So this one has basically generated this flow accumulation raster here. It's if I zoom right, let's see, where's a good place to look? Somewhere up, kind of like at a height of land. Like, yeah, somewhere like this might be good. We're kind of looking at, so this is where two watersheds come up against the boundary between two watersheds, basically. If I stretch that there. So I can see as the water starts, as at the top of the ridge here, let's say, the values for those pixels are very, very low because no flow has accumulated there. But as I move into the channels, I can see the pixel values increasing. And as I move down, so the water is flowing down, 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 I can see all the water from all the pixels above it is flowing into those lower pixels and increasing as we move down the raster. And so as we go down, 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 we can see those numbers getting bigger and bigger and bigger. So hopefully that kind of illustrates the point. This is a flow accumulation raster. The flow has accumulated as we go down the catchment. And I guess one thing to point out about this, so we've got these numbers here. The last pixel I clicked on, 85,000. So these are dimensionless numbers. They don't they reflect the accumulation of the flow from upstream, but not kind of in any real volumetric sense. Like it's not in cubic meters or gigaliters or anything like that. It's really just it's about the addition of basically not arbitrary, but the addition of numbers that don't have a dimension. That's kind of the point here. So so one way that we can look at using this raster is we can hide all the low pixels. So using the same transparency method we used before, we can use the layer styling panel. And if I add a transparent pixel list, what I can do is I can hide all the low flow accumulation pixels. So if I say hide everything from 0 to 1000, let's say, from 0 to 1000, what I can see is, I'll do it this way, turn off a couple of these layers. Okay, so I've hidden all the pixels below 1000. I can only see the ones that are above 1000. And so basically what it means is if I go to the top of, in the higher levels of the catchment, to the top of this drainage, the numbers I'm going to see are sort of nearing 1000. So that means there would be more pixels up here, but I've set 1000 as my threshold there. And so if I can adjust this threshold a little bit, and this is actually a good way for us to start to get a feel for basically where channels might actually, like, persistent perennial streams might actually begin in our landscape, because these perennial streams are the places where we're most likely going to encounter sort of ordinary low level flooding. So if I change that upper limit of my threshold to say 2000, 2000. So I'll do it again. Before it was 1, I'm going to change that to 2000. I can see as I change it to 2000, well, some of those other lower flow pixels get hidden. So change it to 3000. It sort of moves its way down the channels until, and basically what I'm looking for is I'm looking for a threshold that I'm going to use in my analysis. And like I say, kind of the way I'm thinking about it is these perennial streams where they would begin. And so it's a little bit arbitrary. It's a little bit of maybe going back and forth until you get the results you're after. But yeah, anyway, so I'm setting a threshold. I'm going to leave it at about 5,000. I think that's looking pretty good. And maybe one more thing I'll point out here is, so, I mean, at zoomed out scales, at small scales, these channels match the landscape, match the base map quite well. But if I zoom in nice and close, what I'll see is they become very pixelated. They don't actually necessarily follow streams down the center line. And so this is a scale problem. I mean, this is pretty classic GIS issue, is the data that you use, depending on the level of detail and the coarseness, is only going to be usable at certain scales. And so I think this reflects the scale that might be appropriate for our SRTM DEM might be that we might be thinking about, well, if I zoom out to 1 to 100,000, it looks like a reasonably good fit. But if I zoom right in, it means that maybe the SRTM is not quite high resolution enough to meet the needs for very localized mapping, but it's not too bad. It's again, if you have better DEM data for your local area, then you may want to use that for very localized mapping. Okay. All right, so my next move here, I've done steps 1 and 2. I've got a sense for what the flow accumulation means. I've set a threshold. So now I want to define a drainage network. I want to extract the streams from that flow accumulation raster. And this is nice and simple. In the processing toolbox, this one's actually not in the hydrological analysis group. This is in the stream network analysis, I believe, extract streams. And so I'm going to extract streams from my flow accumulation raster. And I'm going to set my channelization threshold. Where do the channels begin? This is the same threshold that I just was looking at using that, that pixel transparency method. So I'm just going to set that the same, 1 to 5,000, or sorry, 5,000. And I'm going to save that to a new raster in my temp folder called extract streams. And this will be very, very quick. And I've got a new raster here called extract streams. And perhaps as expected, it looks pretty much like the same locations as my flow accumulation raster because I've used the same threshold that I was using to visualize it. So a big difference between these two rasters, where the flow accumulation raster, each pixel will have a value representing the accumulated flow from upstream. The extract streams raster is much, much simpler. It's just a 1 indicating the presence of a stream, or a no data when you click off the streams. Pixels off the streams are no data. So it's either it's a stream or it's not a stream, and it doesn't have that extra information about the flow accumulation. But this extract streams raster is very important because basically what it does is it gives us our baseline for the next step of our analysis, which is calculating this height above the nearest drainage, where we need that baseline so that we can say, what is the nearest drainage? Where is the nearest drainage? What's the elevation there? What's the elevation here? And measure that difference. So let's do that 4th step. And that is in, again, back in the hydrological analysis group. And the one we're looking for is elevation above stream. So I'll run that tool. My input DEM file, this will be my breach depressions least cost, my conditioned, my pre-processed raster. So breach depressions least cost. My input streams will be the extract streams that I just created. And my output raster will be, save that with the name of the tool, elevation above stream, and run that one. So that's going to take a few seconds to process. And there we go, close. So I'm just going to bring that down. So I've got to do a little bit of styling here to actually make this make sense. So there's my new raster, elevation above streams, and I'm going to give that some color. Zoom into some areas, sort of mid-catchment, and stretch that raster. And so what we can see is whereas before with the original DEM, all our elevations were in meters above sea level, the pixel values now are in meters above the nearest stream. So for this one, if I sort of click around the pixels, I can see it's just a few meters above the nearest stream. And when I click on the pixels that are on the stream itself, well, they're 0 because they're 0 meters above the stream. They're on the stream. They're exactly on it. So what we see is, as we move away, increasing ever so slightly. And these areas in blue, these are areas that are quite distant from a drainage and quite high elevation. So I can see they're like, in this case, 20, 30 meters. And if we go way up in the mountains, we'll probably see even higher values. So yeah, in the plus 100, 200, 300 meters above the nearest drainage. So at this stage, we're starting to get pretty close to having a bit of an understanding about where the potential for flooding is in our landscape. So if I zoom into a stream and I just do a restretch right there, maybe even a bit closer. So what I can see is the breakdown of classes here. And so basically from 0 to 2 meters is red, 2 meters to 4 meters is yellow. And as I sort of zoom around and restretch, you can see those kind of adjust a little bit. So I can, basically what I want to do is I want to use the visualization here to sort of delineate where I think of as my high-risk flood zones. And I've got to sort of make some assumptions here and take some guesses. So I can go in and I can change these classes, bring that out a bit. So I can change these classes. So maybe I would say, well, let's try 4 meters. And so if my threshold between red and orange is 4 meters, then yeah, I can do it that way. But this is, I'll just point out, this is a linear interpolation. So basically what it's saying is the colors are going to be linearly stretched along that spectrum of colors based on the values that we're seeing here. Another way we can view this, which might help kind of more crisply delineate that risk zone, is if we change our interpolation from linear to discrete. So if we actually set discrete groups, discrete classes where the pixel is either in one group or another. There's no sort of gradation between the groups. And so if I zoom around a little bit, similarly to with the linear interpolation, with the discrete interpolation, I can set my color boundaries, my class boundaries. So if I say, well, let's see what everything, if I set my red class to be everything below, less than or equal to 5 meters, what does that look like? So it's actually showing me quite a lot of land is in that 5 meter, within 5 meters of the height above the drainage zone. So maybe I want to tone that down a little bit. This happens every once in a while. I find that it sort of goes a little bit crazy when you change them. I usually just reset it by choosing the color ramp again. So let's do that again. 4 meters. So now everything up to 4 meters above the drainage is in that red zone, or maybe I even want to try 3, and let's see what that looks like. Okay. So, and maybe we'll take this orange zone and make that more like 10. So we've got 2 classes. We've got, oh shoot, do that again. So 3 for red and 10 for the next one. Do that one more time here. There we go. 3 for red, 10 for orange. Okay, there we go. So now we've got kind of like, we're coming at it sort of like, well, here's a high risk, low risk kind of a classification. And I'm sort of choosing arbitrary numbers here, or I'm sort of taking a guess at the numbers here. But yeah, if we want to do a bit of a deeper analysis, we could do that. Okay, so if I turn on I bring my buildings in. So I've got my OpenStreetMap buildings. Now I can start to get a little bit of a feel for, okay, well, I've got these buildings that are actually in the red zone. These are in a high-risk flood area. If I turn off that elevation above stream for a sec, I can see where these are in the landscape on the aerial photo, and toggle that on and off a little bit. I can get a little bit of a feel for the quality of this analysis and whether I'm sort of picking up on real risks or not. But so yeah, so these are some low-lying areas following drainages, and basically what we're seeing is where the drainage is, it's relatively flat in some of these areas, and so yeah, it stands to reason that these may be fairly high risk for floods. Okay, so I'm going to keep moving here. One thing I wanted to point out about this raster. So if I zoom up to the coast, I can see there are all these chunks taken out of it. So sort of all these areas that are missing. If I look at my original SRTM, I can see those are filled in with pixels. So I've got pixels in those areas. Why aren't they coming through to my elevation above stream raster? And so the reason is it's to do with the thresholds we set for the flow accumulation. And so we've set basically saying, well, I don't want to consider any streams with less than 5,000 flow accumulation in my analysis. But if I dial that down a little bit, I can see now that some of those areas actually do have streams. And so these areas would have pixels that would relate to those streams. So these are basically areas that are within the catchments of those streams that have been obscured by our threshold. And there are, in fact, some buildings in some of those areas that we've got mapped in OpenStreetMap. So I think basically what we're going to have to do here is just sort of keep that in mind when we're doing our analysis. These coastal areas are not going to be addressed by this analysis unless we go back and sort of modify some of our thresholds. Okay. All right, so moving along here. So what can we actually do with this raster now? I mean, I've taken a very quick look at sort of interactively moving around and taking a look at buildings that might be in this red zone. But we can actually use the buildings themselves, the geometries of the buildings themselves, and we can derive those hand or height above nearest drainage values from that raster. And so this is a two-step process. Just going to zoom out, turn off a couple of things here. So right now, what I've got is I've got the buildings for all of Papua New Guinea. So what I want to do is, one, I want to select the buildings that are within my area of interest only. So I'll select by location the buildings that intersect with my AOI, my area of interest. And so those are now selected. If I zoom in, yeah, they're bright yellow. Those are now selected. And then what I want to do is I actually want to convert them to centroids. And the reason is, and if you were with us last week, we did a very similar thing. I want to sample the values from the raster below it, but I can't do that with polygons. What I need is a set of points. So I'm going to convert these buildings to points so that I can sample those values. And I will do that using where is it? Vector, geometry, centroids. There we go. So my input layer is my buildings, only the selected features, and I'm going to save those to, I'm going to create a new geo package. I'm going to save that as my building centroids. So it creates a new set of points for just the buildings that I have selected. Hopefully I've done that right. With any luck, yeah. So it hasn't done it for the ones outside my AOI, just the ones I had selected. And now I can sample those pixel values under each point. And so how do I do that? There is a tool, it's always a tool, raster tools, where is it? Raster analysis. Sample raster values. So I'm going to sample the pixel values in the locations of those points. So my location, my input layer will be my centroids, my raster layer. Now this is my elevation above stream layer. I want to get that hand value for each building. And I'll just make sure that I've got an output column that I recognize the name of. So I'm going to call that hand. And I'll save that to my new geo package called buildings hand. Okay, hopefully this is nice and quick. Oh, that's fast. Oh, spoke too soon. Yeah, there we go. So now I've got a new layer. I've got my centroids, but I've also got this new layer of buildings hand. If I just open up the attribute table there, I can see that I've got these values. So it's picked up the pixel values underneath each point. Interestingly, it's got all these null values. And so what are these? These are those are the buildings that exist in those regions where we don't have pixels. So basically it can't pick up a pixel value because there's no pixel to pick up. So I just want to filter those, like delete those out. So I'm just going to run an expression where I go hand one, the attribute of hand one is null. So I'm just going to select those and just double check. Yep, so that's selected all the ones that are in those no data areas. I'm just going to delete those out of my analysis because they're not going to be useful in this. Okay, so my next step is to actually do something with this data. So I've got all these buildings, the point locations, I've got the values in them, and so I can do some visualization of the patterns in the landscape here using the layer styling for this layer. So one way I can do that is by showing them as, maybe I need to get rid of something here. I think that's a bit too much. There we go. Let's take a look at that. So let's take a look at categorizing the buildings, the new buildings point layer using risk categories. So the way I'll do this, so by default it comes in as a single symbol. I want to change that to graduated renderer, and I will classify it based on the value of the hand column. So if I classify that, okay, so now I can see I've got, by default, I've got 5 categories. I want to break this down a little bit more simply. I just want to have low, medium, high. So I'm just going to have 3 classes. And I want to use, rather than color, I'll use the size method. So I want because what I want to do here is sort of emphasize the buildings that have the highest risk, the ones that are closest to those drainages. So I'm going to make those ones, the ones in the high risk areas, larger. And so what I'm seeing here right now is the size. I've got the sizes the wrong way around, so I need to switch this. So I'm going to change my sizes. Instead of 1 to 8, smaller to larger, I'm going to change that from larger to smaller, and I'll use something a bit smaller than 8 because I think I use 3 and 0.5. And so now I've got my 3 categories. And then I want to change these a little bit more. So I've got my first category is 0 to 20. And if we recall, looking at the elevation above stream values, 20 would be really high. So that's 20 meters above the drainage is very, very high. So I'm actually not considering those to be high risk. So I really want to focus on the ones that are down low. So I'm going to change my values, class breaks, so that it's not 20 meters, but let's just say 3 meters. So anything from 0 to 3 would be considered high risk. And then my second category, medium risk, I'm going to say 3 meters to 10 meters. So anything in the 3 meter to 10 meter range, that's my high risk zone. And then let's see, just a couple little things I can do here. I can change the values in the legend. So I can say that's high risk, less than 3 meters. Medium risk, 3 to 10 meters, and this would be low risk, greater than 10 meters. And then I can change those symbols, so maybe I'll just use red because it's such a risky color. And my medium, I'll change that to something a little more orangey. And then the little ones barely even matter because you can barely see them. So one last thing I'll do there is I'll just change my symbol levels so that the high risk ones sit on top. So I'm just going to put the high risk ones up on level 3, medium on level 2, and low risk on level 1. Okay, and so now my high risk ones are standing out in front of everything else. And if I wanted to even just sort of tone down the map here, maybe I'm not even worried about the low risk ones, I can just turn those off. And then only the high risk ones and the medium risk ones are left behind. So that'd be one way of styling that. On a layer in QGIS, we can have multiple styles associated with it. So I want to add one more style to this layer, and then we can look at switching between them. And so with this one here, in the layer styling panel, there's this cool style manager tab. By default, you have one style on a layer called default. I'm just going to rename that to risk categories. And I'm going to add a second style that we can then switch to. And I'm going to call this one proportional size, something like that. So this one I'm going to style a bit differently. And this one, rather than a graduated renderer, I'm just going to use a single symbol, and I need to change some colors here. So I'm going to make this kind of like a bright blue, and maybe I want to actually optimize this for sitting on top of an aerial photo. So I'm going to make that bright blue. I'm going to drag that color from the fill to the stroke, and then I will tone down the fill there quite a bit, so it's almost transparent. So so I've kind of got all these symbols. They're all the same size. They're all 3 millimeters. But what I can do is I can use this data-defined override to write an expression to set the size of my symbols. So I'm going to write an expression here. And I'm going to use an expression to set the size in millimeters. So I want to use an attribute, my attribute hand1, but I don't want to use increasing size of hand1 to mean an increasing point. I want it to be quite the opposite. So I'm going to choose the inverse of hand1, which is 1 divided by hand1. And then since I'm talking about millimeters, I'm looking at the preview value here, 12,500. I know that's going to be way too big, so I'm just going to add a multiplier just to bring the size of that down quite a bit. So I'll just add 0.0001. So there's my expression. If I click on OK, it's going to use that expression to symbolize all of the points. And then by doing that, I can zoom way out and I can see sort of where the concentrations of buildings at high risk are. So if let's see, I put that back on. Yeah, and so I can see the ones that are very, very low risk, according to this model, just sort of disappear. The ones that are highest risk kind of stand out very strongly. And so what I can see is, so these ones that are closest here, these probably have a very high, or very low, I should say, hand value. And yeah, so that's like 10 times, to the -6. So that's like, yeah, so that's practically at 0. And as they move farther away, they get kind of lower numbers. Okay. Right. So I've got my two styles, and I just want to basically show you that when you have those two styles, you can come back into the style manager and just toggle between them. So there's my risk categories style, or I can switch back to proportional size style. So whichever one suits my visualization purpose. They're both saved against that layer. I can also right click on the layer, go under styles, and switch between them there. Okay, so another thing that we can use this hand layer for. So we've used it to sort of identify the buildings that are at risk. We can also identify road access that may be at risk, because roads can get cut off where roads pass through low-lying areas. And so maybe what we want to do is find all the locations where that's at highest risk. And so I'm going to bring in my OpenStreetMap roads, also from the GeoFabric extract. There it is there. And bear with me for a moment. Okay. So I've got all my roads, and again, this is the countrywide roads data set. I'm only interested in the ones in our area of interest. So I'm just going to do a quick clip on those. So I'll go under Vector, Geoprocessing Tools, Clip, and I'm just going to clip that layer with my AOI. And I know I've got another step after this, so I'm just going to leave that as a temporary layer for the moment. Okay, so now I've got my clipped version, which is just the roads in this area. And so I want to narrow this down a little bit further. Not only am I only interested in the roads in this area, I'm also only interested in certain types of roads. So there are lots and lots and lots of roads in this data set. Some of them are footpaths, some of them are basically different types. So I'll just do a quick categorization so I can actually see what the types are. So I know it's the F-class attribute. So I can see we've got footways, paths, service roads, unclassified, and so on. The ones I'm most interested in here are the primary, secondary, and tertiary ones. This may be different for any given local area, but just for the sake of argument for this analysis, I'm just going to narrow it down to just those primary, secondary, tertiary ones. So I'm going to select those using an expression. My expression will be f-class in, and then a list of the possible values. So primary, comma, secondary, comma, tertiary. So that's my expression to select just those roads. So I'll select those features. And so it's selected them in yellow. And then what I want to do is I want to export those selected features. I'll export them into my analysis geopackage, and I'll call it AOI roads. Maybe I'll call it roads AOI. And then the other thing I want to do here is I want to change the coordinate system. But by default, when I bring in this layer, it's in EPSG 4326, which is a lat-long projection. The coordinates are in degrees. But the next step I want to do is I want to break up the road segments into points measured in a distance of meters. So what I want to do is actually convert this layer as I'm exporting it into a meters-based projection. And I'm going to use the PNG 94 zone 54 UTM-based projection that is measured in meters. So I'm going to convert that to meters. Save only select features, yes. I think the rest is probably fine. Let's find out. Click OK. Okay, and now I've got a new layer that's just, I'll make that black and a bit thicker so we can see it. And so now we've got basically a set of access roads that we can use for our analysis. So the next step here is I want to convert. Basically, I need to do the same trick that I just did, where I overlay. No, not that one. This layer here, where I overlay these tracks with the pixels in this raster and identify the locations where they're really low lying. So I think there are probably a few ways of doing this, but the way that occurred to me for this was to break the roads, or to basically drop a series of points along every road at a spacing of a certain number of meters, and then use those points to sample from the raster. And so the tool I'm going to use here is called Points Along Geometry. Let's see if I can remember where it is. No. Is this it? Here we go, yeah. So it's in the vector geometry section. Points along geometry. My input layer is the roads AOI. My distance, my spacing for these points that I'm going to generate is, I'm going to use, well, the pixels are 30 meters. So nominally I could probably use 30 meter spacing for these points. So I think I'll go ahead and do that. Yeah, your mileage may vary here, but yeah, that's my basis for choosing 30 meters. And let's see, do I want to, maybe I know my next step will be to sample, so I don't need to save this into a geopackage. I'm just going to save it as a temporary layer, so I'll run that. Okay, and now I've got basically over the whole analysis area, I've got these points at 30 meter spacing along every road. And so my next step is to do the sample raster. I'm just going to type it up here to find it quickly. So my sample raster values, so that I can grab those pixels, the pixel values from the underlying raster. So that's interpolated points. My raster layer is elevation above stream. That's my hand raster. And my output column prefix, I'm going to call this again hand underscore. Okay. So I will save that to a geopackage. I'm going to call the layer roads points hand and run that. Oh, where did it go? Oh, I ran into a problem with this before. Okay, well, let me try. I think my problem here is for some reason it's not picking them up because this is a memory layer. So what I'm going to do is export those points. Hopefully this works. It's going to call the interpolated points. I'm going to call them road points. Click OK. All right, so I can see those, and then I'll try sampling those ones. So road points, raster layer is elevation above stream. Call it hand. And let's see if we can make this work. So roads, points, hand, fingers crossed. Great, I can see the points there. Okay, phew. And so now if I look in that geopackage layer, I can see I've got all my points from the roads with a hand one column. So again, we're going to have that same problem where some of the points are going to be nulls. So I'm just going to filter those out quickly. So hand one is null. Select those features. We'll have a heap of them along the coast. So I'm going to delete those features. And what's next? So now I've got my points, all my points with a hand value. And essentially what I want to do now is really I just want to keep the ones that have high risk value. So these are the ones that basically intersect these red areas here, these ones that have a hand value of 3 or less. And so can use one of the methods we used. We can select them and export them to a new layer, or we can just filter them in place. So I'm going to choose that. I'm going to right click on the layer, filter it. I'm going to choose for my expression, I'm going to say hand one is less than or equal to 3. So that's my height above normal drainage. Height above normal drainage for that point is less than or equal to 3. And now we can only see the ones on the map that intersect with those red areas. So this is making sense. And so I guess just to finish that one off, I'm going to, what am I going to do with this one? I'm going to make it just to differentiate from the building points, I'm going to make those hot pink diamonds and make them a little bit bigger. There we go. And so now, as we zoom out, maybe I'll tone this down a little bit so those points stand out a bit better. Yeah, and so now we can see we've got buildings where we've identified higher risk buildings. We've got potential road accesses that are at risk of flooding. So that's a very sort of quick run through this analysis. Kind of treated a few of the things that you need to probably think about a little deeper, rather superficially. You could take it further by perhaps, by taking the frequency distribution of the heights in our area of interest and characterizing them such that you can determine with better accuracy what is the boundary between a flood risk zone. So I've just sort of chosen 3 meters, but maybe it's 2 meters, maybe it's 5 meters. Is 3 meters the right cutoff? So big question there. We need to think about, would this be better if we had a high resolution DEM? So maybe if we were working in more localized areas, if we had high resolution DEMs, we might get better results. Question to ask, so where there are concentrations of vulnerable buildings, is it because we've mapped more buildings or is it because they're more vulnerable? So I'm noticing like there are big areas in the south here that I don't see any buildings at all. Is that because there aren't any buildings or we just haven't mapped them? So, and I guess one other factor that I definitely think worth mentioning is this is a pretty much a one-dimensional flood risk model. A more sophisticated model might take into account, the local soils and the vegetation in the area, the land use patterns, and climate factors. So there might, to do a full sort of flood risk analysis, I think you'd want to go deeper than we've just done here. But hopefully this really illustrates the point. So, what else? Is there anything else to say about any of that? Well, may the force be with you, of course. Miko, do we want to do questions, or do we want to, should I spend a couple of minutes on a satellite imagery?
Okay, let me just go ahead if there are any questions I could see here. Okay. Let's see here. So there's a question. There's pretty much not much question, but more of a request. Can you share publications on terrain-based analysis for flood analysis, things like that? But yeah, any questions, folks, so that we can ask it directly to John? More of comments.
So the with regard to the articles, so the article that this analysis is based on, the citation is down at the bottom there. It's called Height Above the Nearest Drainage, a hydrologically relevant new terrain model. So you should be able to find that one pretty easily, I would say. The URL to the reference is there as well.
So there was a question here. Do you have any idea on areas of mass flooding? From Mikel.
Can
Can
I'm not sure I know the question, understand the question. Areas
yeah.
of mass flooding.
Yes, Philip. Feel free to chat your question. Philip. Mikel, can you elaborate your question? Yeah, I don't think. Yeah, maybe. Can we
I know,
use? Yeah,
I know, Michelle. We'll have to take it up at the next GeoGeeks.
yeah. um, from Ponzi, can we use in a safe to continue analysis for flood data that we have already gotten from that DEM?
Oh, I wish I knew the answer to that. I've actually never used the InnoSafe plugin, but I understand there was some recent training on it, so I'm gonna have to catch up on that.
Yeah, I'll be sharing that participant form very soon. Yeah, I don't think there are any more questions for now, but feel free to put the questions here and then I might email it to John and then we could catch up later on. Another one, last one, John. Can we do this with LiDAR imagery? What would be different?
I mean, that's a good question. So not something I'm necessarily an expert in, but I think my approach to that has been and would be to convert the LiDAR to a DEM, to like a sort of a 2.5 dimensional raster rather than the sort of 3D point clouds, and use the same kind of tools as we've been doing here. So yeah, I think that I would probably convert it to this DEM format from a LiDAR.
Last question. Sorry, John. The questions are now raining and it's flooding. How does the elevation work in areas between two streams if the streams are of significant elevation difference?
So okay, so yeah, interesting question. I mean, I think, so if I'm understanding how this model works correctly, where am I here? So if we have an area, if we have a point that's sort of between two streams, I think the first thing it does is it sort of figures out, for this pixel here, which is the nearest drainage, and then it calculates the vertical distance between that point, that pixel, and the nearest drainage. So I think every pixel, like there will be a deterministic which is the nearest drainage. So I think that's probably, hopefully that's kind of the answer to the question. Yeah.
What is the difference between GeoPackage and yeah, you know this.
Don't get me started. Okay, well, shapefiles, I mean, they've been around forever. They're sort of like the cockroach of GIS. They will never die. So because they've been around for so long, lots of software is configured and built to actually be able to use shapefiles. And they're very robust. I guess some of the shortcomings, like they can only handle up to about 2 gigabytes of data. So for most people and most purposes, that's probably big enough. But if you have anything larger, then you're going to hit the limits of the shapefile. One of the really annoying things about the shapefile also is that the column names are only limited to 10 characters wide. So like not the contents of the attributes, but the actual name of the column. And so if you have a longer column name in a different format and you export it to a shapefile, it's going to truncate that column name. So this can sometimes get confusing when you have similarly named columns and they all get truncated to something very, very similar. Geopackages, I think, you know, like they can contain multiple formats, raster, vector. You can also store like default styles and things like that, and QGIS projects even in a geopackage. You can, I think, you know, they've got nice built-in indexing and anyway, yeah. So I guess there are multiple advantages, but I think for a lot of people, one of the big advantages of the shapefile is that it is so interoperable. You can use it in so many different types of software, and so my usual go-to is I work in geopackages. If somebody asks for data, quite often I'll give it to them as a shapefile because it may be more suitable to their software. What else we got?
Yeah. We still have. Do you think we still have time to accommodate a few more questions, John, or do you
Yeah,
want to proceed with
yeah,
it?
yeah.
Okay.
I'm happy. Yeah.
Okay. From Mungkaila, can we export the drainage network to become a shapefile?
So that's a very good question. I think we could give it a shot. So uh, we can. Oh well, I actually don't know off the top of my head what the tools are, but I would almost guarantee there would be something in. So vector stream network analysis in the white box tools. I think that we could probably there's probably a tool in here that we can extract this as a vector. Almost undoubtedly, I've definitely done it in other packages like Saga tools, which is another similar to white box tools, a plugin for QGIS. Yeah, so it is definitely possible.
Okay. Can we use this analysis in areas that have a lot of streams but relatively flat?
Sorry, just 1 second. I saw Michelle had commented their white box tools raster streams to vector. So I think Mankala, that's probably the answer to your question. We could take this streams raster and convert it using this tool here. Thanks, Michelle. Sorry, Miko.
Yeah. From Uji, can we use this analysis in areas that have a lot of streams but relatively flat?
Oh yeah, that's a really good question. So I mean, I think, yeah, I would tend to think that DEM-based hydrological analysis will probably work better where you have more sort of terrain, more topography. So flat areas. I would suppose that the quality of your data would become really, really important. So like the precision and accuracy of your DEM. I would think that SRTM may not be at all suitable for areas that are very flat. But yeah, if you had a really good DEM, I would imagine you would probably be able to get some decent results. But yeah, I think it's a question of giving it a shot and seeing what you can do. I mean, as you've seen, it's a pretty quick and easy thing to do to actually run this analysis. So if I had a good DM, I'd definitely be taking a shot at it.
Thank you, John. There are more questions. Amas, this is a good topic that you're proposing. I for those kinds of topics that you'd be interested more to listen about, like I think we'll be able to bring up a better case if you could put it in the feedback form so that I know. Oh, hey, John, we need more training. Yeah. Yeah. Feel free to put your questions as well in the feedback form or in the chat. We'll get to you. Do you have anything to continue with, John, for the next topic?
So for the next topic, like for this session, or
Yeah, for this session. I mean, yeah.
I think we should not go there because it's probably going to take a little bit longer.
Okay.
And
Yeah.
so yeah, I think we should save it for another session. But yeah, so what I was going to talk about was using Sentinel data and doing some flood mapping using that. But I think it'd be better just do it another time.
Yeah. I do agree. Since we're lagging out of time. So thank you so much, John. So for the other questions, I'll send it to John so that he can reply it via email and reply to your questions. So I'll just wrap things up with a few announcements. So if you have any training topics that you would like to pitch in and we could find a trainer or possibly John again, feel free to put it in our feedback form. It will definitely build us a case to produce a Dutch training again. So yes, thank you again very much, John. Let's catch up after this call in next week. But I'll be more than happy to share some announcements. Is it okay?
Thank you so much.
Yeah, I'll share my screen, John.
Okay. Oh, yeah. Do I have to stop? Yeah.
Yeah, there we go. So let's see here. Is it sharing? Is it sharing? Yeah. Okay, here we go. So for tomorrow we will have two more. We'll have more trainings on OpenStreetMap and open mapping related. So I'm just going to highlight tomorrow. We will have data mining with OpenMap data using Overpass. And feel free to register in the same link that you signed up where John's training was registering. We also have a mapathon tomorrow for Bhutan, led by one of our gurus here. Guru Sonam, are you there? Yes, I think he's here a while ago. So we'll be having a mapathon for some areas in Bhutan. So if you'd like to join, learn how to contribute to OpenStreetMap, and see how the data like John was sharing about the building footprints a while ago, how it's being produced in real time and being able to use it immediately, please join us in the mapathons that we're having. For the question, are the ET certificates for previous training sessions already emailed? No, Loris, unfortunately, we haven't emailed it. We usually send it out on the last day of each month. So if you don't receive your certificate by that, feel free to email me so that I could check if there's anything wrong. For those who would want to help, our Papua New Guinea project for MapSwipe, if you haven't downloaded it, feel free to download it on your mobile phone. You're helping the mappers digitize it faster. So download MapSwipe and help us locate building footprints or locations of buildings in Papua New Guinea so that we can digitize it faster. So if you are part of an NGO, a CSO, or the academe, and you would want to have a demo on a mapathon or about OpenStreetMap, let's get you an open mapping guru. We'll be hosting free demo sessions for anyone who's requesting. Let's contact me in my email, miko.tamura@hotosm.org, and let's schedule your first mapathon with your team. Yeah, feel free to reach out via Slack. So if you have more questions, most of the guru open mapping gurus and the tech team and data team from HOT are in Slack. So feel free to join and reach out to us with lean.dehont@hotosm.org or openmappinghubap@hotosm.org. John, if you'd like to add your email in the chat so that if people would like to uh, reach out to you and say thank you, or maybe they want
Sure.
another training with you and their team, feel free to drop your email. Yeah.
All right. Done.
For those who needs to register for the Overpass Turbo, feel free to go to the Open Mapping Hub Asia Pacific page. The registration link is there so that I can share it to you. Yes. Any more questions? Have a great evening, everyone, folks. I hope to see you soon for the next iteration of our tech and data trainings. Hopefully, we would be launching our second season, but I need to find the trainers first. So thank you again, John, and thank you for everyone who joined us today.
Thanks, everybody. Have a great weekend.